everyone, here is the video on independent assortment that I promised you. I apologize for the low production values. I have never done a video like this before. But let's get started, and we're going to consider what we would expect to see under independent assortment and then under deviations from independent assortment. So under independent assortment, we're going to assume that we have the parental generations, and they are true breeding parental generations right here. So we have dominant homozygotes for both kinds of alleles. If we do that parental cross, we get an F1 that is the hybrid, or heterozygotes. Then if you assume that we're going to do an F1 cross, so self-crossing the F1 generation, then we're crossing the heterozygotes with each other. Now what independent assortment assumes is basically that these genes are found on different chromosomes. So I'm going to put the two different alleles for the gene of A on one chromosome and the two alleles for gene B on the other chromosome. Now if we replicate the DNA here in preparation for meiosis, then this is what it would look like. We're going to have a dominant allele on each of the sister chromatids of this chromosome, and then the recessive allele on each of the chromatids for this chromosome, and the same for the other chromosome that holds the gene for B. Now if these two genes are on different chromosomes, then what we expect in terms of gametes is this. We expect that any one of these combinations is equally likely. So big A with big B, big A little b, little a big B, and little a little b. Because they're on different chromosomes, we don't expect there's any reason for those genes to travel together into the gametes. Under that circumstance, you would expect this kind of a dihybrid cross Punnett square, and ultimately, if you filled this in, what you would expect to find is that 9:3 to 3:1 phenotypic ratio. Keep in mind that that is for an F1 self-cross and not a test cross. So keep your eye out for that. If I were to have said that we're going to cross the F1 with a homozygote recessive, then you would not expect this 9:3 to 3:1 ratio. So always pay attention to what's being asked. All right, so let's contrast that with the dependent assortment right here. The same setup. We have the parental generation. We have the F1 hybrid. We're going to do a self-cross. But under dependent assortment, and I'm going to clarify here that what I mean by that is that these two genes are completely dependent on each other. They will segregate together. So I've tried to illustrate that here by putting them, first of all, on the same chromosome. I've left this other chromosome here just to make it clear that this is still the same individual with two chromosomes, two of each. But these two genes are on the same chromosome, and not only that, but they're really close together. So when we get DNA replication, we'll just have the same thing. We will have the dominant alleles together on the same chromosome, the recessive alleles together on that chromosome, that homologous chromosome. Now, what we expect under dependent assortment is essentially, as I said, that they're going to travel together. So this individual is going to make these kinds of gametes. Essentially, the big A, big B allele combination will always stick together. So here and here. The little a, little b allele combination will always stick together, so here and here. So really it's the same as just having two kinds of gametes, big A, big B, little a, little b. So to clarify again, what I mean by dependent assortment is that those genes are always traveling together, and what you end up with is essentially a cross that is the same as if this was a monohybrid cross, because those two genes are so closely linked physically on the chromosome that they travel together and they behave as if they were one gene. Okay, so that's what I mean when I say dependent assortment, meaning that it's completely dependent. Okay, so let's think about what happens when it's something in between. Sorry again for the very poor production values. Something in between independent and dependent assortment. Again, it's the same setup. We have the parental generation is two true breeding varieties. The F1 is the hybrid or heterozygote. If we do a self-cross, this is what we're going to look for. So essentially, I've set this up in the same way. Here's the F1. This is the genotype of the F1. But I've tried to indicate those two genes on the same chromosome, but not as closely linked as under dependent assortment. There's a little bit more space between those genes. So now we're going to replicate. We're going to have those different alleles on the different chromosomes. But if we're not assuming independent assortment, and we're not assuming dependent assortment, then here's what we expect. So we may still get all different kinds of the gametes. So big A, big B, which you should note is a parental combination. That is a combination of alleles that was found in the parental generation. Big A, little b, which is now a recombinant combination. So this combination of the big A and the little b alleles was not found in the parental generation. The same for this combination, little a, big B, was not found in the parental generation, so it's recombinant. Little a, little b was found in the parental generation, so it's parental. Okay. All right. So let's consider this first. If the parental and the recombinant allele combinations were equally likely, then it might look like this. I've just made this conveniently add up to 100 to make it simple, easy to see. So we have this combination you find in 25 of the offspring, this in 25, this in 25, and this parental one in 25. So that all adds up to 100. These are the two recombinants. That's 50. So 50 over all of them, or 100, is 50%. So this is that 50% recombination frequency. Remember I mentioned that that was the maximum recombination frequency. And if you look back to the beginning of the video, you'll see that this is essentially what we expect under independent assortment. But if what we see is something else, then what we're seeing is something in between independent and dependent assortment. So here we have this parental allele combination found in 40 individuals, this recombinant one in 10, the other recombinant one in 10, and the other parental combination in 40. These two recombinant combinations are found in 20 individuals. Again, this adds up to 100. So 20 divided by 100, this is a 20% recombination frequency. What this essentially means, this is the last page here, is that at some point there was a crossing over event during gamete formation, so that led to a new combination. big A and the little b allele here. So let me pull that down. We had a crossing over event. So now we have into one gamete is going to be this parental combination. Into the other gamete will be this recombinant combination. And it's recombinant because it's the result of this crossing over event where the two homologous chromosomes share DNA, switched alleles. You have this other recombinant combination that results as well from this same crossing over event, and then this final parental combination. So this crossing over event created this recombinant allele combinations, and that 20% reflects how likely it is that the crossing over event happened given the distance between the genes for A and B. And that's why recombination frequency is a measure of the distance between genes on chromosomes. I hope that helps clear things up. Please let me know if you have more questions.